Welcome to another video from Roland Mösel, founder of Planetary Engineering Group Earth. Minus 250% CO2 emission. Yes, minus 250% until we reach again 350 ppm. Zero emission is really not enough because we are not alone here. There's also nature. And nature was until now so nice to absorb about 20 billion tons of CO2 emissions per year. But this can change quickly. What if nature emits instead of absorbing CO2 emissions? Maybe 10, 20, 30, 40 billion tons per year of CO2 equivalent. Remember, methane is much more powerful as a greenhouse gas than CO2. First time I mentioned this theme in February 2008. CO2 reduction. No, not our emissions. We have to reduce the CO2 in the atmosphere. In February 2009, I wrote about CO2 interest. Yes, let's look on the CO2 emission like a loan. You have to pay back the loan, but not the loan alone. You have to pay back also the interest. And when our CO2 emissions change the climate so much that the permafrost melts and emissions from methane hydrate, then we have a big problem. And this can be a big interest for our loan of CO2. 2013, I wrote my second book, Calculation Error, and headline was Ready for the Climate Maximum Credible Accident Challenge. What happens if nature emits 30, 40 billion tons of CO2 equivalent per year? We have to be able to deal with this problem. Currently, we see strange diagrams. The best of these diagrams goes down to maybe 8 gigatons per year in the year 2100. It is very rare that I see diagrams where it goes in the negative. But when I look at the big blue line, the negative is only minus 10 billion tons per year. So now, how to get this CO2 out of the atmosphere? We know how much is in it. We know how many cubic meters of air we have to move through a filter to get a certain amount of CO2. I analyzed from different companies which are engaged in direct air capture of CO2, what their systems have energy consumption. And I think 1.5 kilowatt hours electricity for 1 kilo CO2 is a realistic assumption for this. Then what do with the CO2? We don't put it somewhere away or something like this. No, we should use it. And to use it, we have to split it again in carbon and in oxygen. And because we know exactly how much burning brings energy, here we can calculate. And in this case, the efficiency is against us. So we have to invest more energy to split it than in the combustion was given away. And so I calculate with 4.5 kilowatt hours per kilo CO2 to split it in carbon and oxygen. So in total, 6 kilowatt hours per kilo CO2, and multiply this with emissions above 30 billion tons per year. This takes a lot of energy. How to get this energy? The only option for this is photovoltaic. As I started to write my first book, Advanced to Solar Age, in the year 1992, I found somewhere a diagram, and this diagram tells us, in 1990, the world production of photovoltaic was 50 megawatt. Now it's between 100 and 150 gigawatt. Let's assume every 3 years the production doubles. In this case, from 1990 to 2020, we have 10 times double. This is 2 power 10, 1024. And so it should be with each 3 year double about 50 gigawatt photovoltaic per year. It's even a little bit more, so the industry managed it to double in less than 3 years. 1996, I made a prognosis of the world production of photovoltaic. In this prognosis, I was the highest of all prognoses in these years and maybe also some years later. I assumed a huge increase of photovoltaic industry, but even here I was wrong, because when I look to 2020, it is about 70 to 80 gigawatt, but in reality it's about 130 gigawatt. So even my very optimistic and very strong prognosis of the development of the photovoltaic world market was a little bit too smaller than it was in reality. So now about the model. You see the results on the first page. We have first an electricity consumption of the mankind of 60 petawatt hours. Yes, I know the electricity is only about 30 petawatt hours, but I calculated each usage of thermal energy, how much to replace it with electricity. And so I assumed the energy consumed of mankind, 60 petawatt hours, will increase a little bit to 80 petawatt hours. But here is not the construction of all the necessary photovoltaic, all the batteries, all the direct air capture, and all the units to split the CO2 into C and O. The blue line is the civilization without this. The red line is to make all the equipment for the planet renovation. And the yellow one is the electricity production by photovoltaic. You see, it starts like an exponential curve, because I assume about 26% increase per year of the photovoltaic production. And when it's really huge, about 100 times of today's production, the yearly increase decreases until we have a limit, and that's enough. But you see, it's very high energy production by photovoltaic. How much CO2 is replaced by 1 kilowatt hour of electricity from photovoltaic? It starts maybe much higher. When there would be only lignite power plants, it would be 1,100 grams per kilowatt hour. Today we are maybe in the range of 680 grams per kilowatt hour, and this decreases. You replace things what are today relatively clean, but maybe combined cycle power plant, 350 grams CO2 per kilowatt hour. All this gets replaced, and in the end, we need 6 kilowatt hours to filter out and split 1 kilo CO2 out of the atmosphere. And here, only 167 grams CO2 are reduced by 1 kilowatt hour of electricity. We start now with the naive scenario. Nature absorbs 20 billion tons of CO2 per year, and if nature didn't die, it will continue for eternity. This is a real nonsense, because today we know that some areas on the planet already turn from CO2 emission absorbing to emitting. In this case, all this equipment would be completely overdimensioned, because we would be finished in the year 2061. Now, another scenario. The nature changes from minus 20 billion tons CO2 per year to plus 20 billion tons CO2 per year, and changes at a rate of 1 gigaton per year. So the blue line, emission of civilization, the red line, emission of nature, and the yellow line is how much CO2 is more in the atmosphere than it would be at 350 ppm. And in this case, we would be finished in the year 2092. In the next scenario, nature changes with 2 gigatons per year until the emission is 30 gigatons per year, nearly what mankind emission is today. And in this case, we are finished only in the year 2135. And but what happens when nature emits 40 gigatons CO2 equivalent per year? You remember, methane is much more powerful as a greenhouse gas than CO2. Oh, we would be only at the end of this scenario at about 465 ppm, much more than we have today. So here we are nearly in a range where also that minus 250% is not enough. What to do with the carbon captured from the atmosphere? Today, mankind produces 4.4 billion tons of concrete per year, 1.81 billion tons of steel, and the rest is insignificant quantities. Alone, when we split 33 gigatons of CO2 in carbon and oxygen, we have 9 gigatons of carbon from this. And we will make carbon as a standard material for construction, for everything. We will make cars of it, trains of it. Now maybe somebody says, oh, carbon, very, very expensive to produce. It's not realistic. No. Here we are in Berlin at the InnoTrans 2018. Who would have thought to make a underground train out of carbon fiber? Nobody. But the Chinese did it. They make a train out of it, and it's clearly they are preparing for a future where we have to capture a lot of CO2 out of the atmosphere, and carbon becomes a standard material for everything. We make bridges with it. Instead of steel, we use carbon fiber. So the energy consumed for only CO2 handling. So we filter and split 50 gigatons per year out of the atmosphere, and times 6 kilowatt hours, this is 300 petawatt hours per year, about 10 times current electricity production of mankind, but all very clean electric power from photovoltaic, and all the photovoltaic is produced by electricity from photovoltaic, so it's clean. Then we want to fly airplanes on long ranges, we want to have ships, and for this is additional 5 gigatons CO2 per year, and we need about 30 petawatt hours per year to do this. And then other plants. I assume 40 gigatons per year for the production of plants. And because in this case we need only the direct air capture and the rest makes the plant, only 60 petawatt hours per year. But why? For the plants. Plants have photosynthesis. They can do the CO2 handling by themselves. Why should we use 60 petawatt hours for CO2 for plants? We have here a very similar problem as at the horse. The horse can run self. The horse can even pull a vehicle behind. Yes, the horse can do it, but the horse is much too slow, and the horse has no endurance. Every 60 kilometers, a horse changed stations. This was standard some 100 years ago. So today, most times horses are pulled in horse carriages behind a big car with hundreds of horsepowers. And similar it is with the plants. In October 2019, I meet an industrial from Jordan. In this case, sure, the first thing I do, I try to sell houses. And one big problem in Jordan, this is a very dry country, is they can produce only very little of their food themselves. They have to import most of their food because they have not enough water to grow plants. And in 2020, I see there is vertical gardening aeroponic, and I thought, problem is solved, great. And I asked somebody, how much can I grow in a glass house with 100 cubic meters? And he told me, this is enough for 3 tons of vegetables and fruits. Oh, great, this is the solution. But then I made calculations how much air exchange is necessary. Outside air goes into the glass house, and a part of the CO2 is absorbed by the plants for growing, and then the air goes again out of the glass house. And there is about 100 times more air exchange necessary that is usually for living. And then I make a calculation. Okay, we have 35-degree hot air with 20% humidity, and this goes in the glass house, and the plants emit much water damp, and it goes out with 70% humidity. And every air exchange would in this case take 2 liters of water out of the glass house. And when I multiply how much air exchange is necessary, I came to the same numbers as is published in the internet. For example, 180 liters of water for 1 kilo of tomatoes. So there are 3 solutions for this. First, to supply the glass house with 500 cubic meters of water per year. That's impossible here. Second solution, recover from exhaust air 500 cubic meter per year. And third solution, direct air capture. Nearly no air exchange in the glass house. I put only the CO2 inside and limit the oxygen of maybe 25%, so very, very few turnaround of the air in the glass house. And I made the calculation for the moisture recovery from exhaust air. And the energy numbers are frustrating high. This is not a good way because it takes so much energy to take out the moisture of the exhaust air. And direct air capture and to blow in concentrated CO2 into the glass house, seems to be a much more energy efficient way to do this. And okay, Jordan is a very dry country, but look at the west of United States. It's now a very dry country, comparable to Jordan. And the development can lead to the situations that we lose very much land for agriculture because it becomes more and more dry. So I calculate for so much electricity to support plants with CO2. On the left side, you see current world production of electricity, about 30 petawatt hours per year. 100% renewable energy on a low level would be about 60 petawatt hours. We replace all what we make fire now with electricity, electric cars, heat pumps, and so on, and we end with about 60 petawatt hours of electricity per year. Then we add power to fuel, we add power to support the growing of plants in glasshouses, and in this case we are at about 150 petawatt hours per year. Suitable for the planet renovation is a range of 400 to 600 petawatt hours per year. So 100% renewable energy is only a step in between. It's only about 1 magnitude less than we need. So we should not concentrate on the target of 100% renewable energy. We should aim much higher, 1 magnitude higher. We should aim for the planet renovation. This was another video from Roland Mösel, founder of Planetary Engineering Group Earth. And as always, like, comment, subscribe, hit the bell to be notified when I make my next video.